Hello students, welcome to the course Electrical Circuit and Network. Myself Milan Sasmal, Faculty of Electrical Engineering Department from JIS College of Engineering. And today we will discuss the Laplace transformation for electrical circuit and for different theorems like initial value theorems and final value theorems. And whatever problem we have solved in last class, the same problem we will discuss also in the light of this final value theorem and initial value theorem, and we will check whether the results are same or not. Okay students, so we will discuss the initial value theorem, that is generally denoted as a IVT, and final value theorem, this is generally denoted as a FVT. For initial value theorem, it's nothing, just to concentrate the idea for the initial condition. Suppose the circuit contains inductor and capacitor. If inductor and capacitor they are previously charged, or some amount of previous voltage within the capacitor, or some amount of previous current within the inductor, then we can apply this theorem to easily find out the initial condition of the circuit. Similarly, for final value theorem, uh, at infinite time, it means suppose after switching for any circuit at the infinite time, what will be the condition of the circuit, that we can find out by this theorem. And for initial value theorem, one thing is very clear, that this theorem has a valid if it is if and only if it's valid if uh, there is no more impulse function. If the circuit contains any impulse function or like that, then we cannot apply this initial values of theorem. And for this final value theorem, this theorem is valid if and only if all but one of the pole of f of s are in the left half of the complex plane, or it can be said as the one of the pole which lies in the left half of the s plane. Left half of the s plane means, if we consider generally a normal plane, in normally like that, left half means, this is the normally our real axis, positive real axis, this is our positive real axis, if we consider as a positive real axis, and this is our j omega axis, positive j omega axis, j omega, and positive j omega axis. So left half means this side, it means it may obtain any of this region. So one of the poles must should lies in this region, left half of the s plane, then only we can apply the initial value, the final value theorem. It's the important criteria that we have to remember. And sometimes in our exam they may ask that write down the initial and final value theorem. So simply we can write down that for initial value theorem, it states that the limit t tends to 0 positive, it means just at the starting point, then f of t, the function f of t is equals to limit s tends to infinity, and s f of s. This is the as per initial value theorem. Now we will see one example, or the previous day whatever the example we have considered, the same example we will considering again to check the answer, and to check it again for this initial value theorem and for the final value theorem also. Okay, so for previous class, whatever we have seen for previously. Okay, so in last class, whatever we have calculated for this I1s and I2s, we have these types of problem is given over there, that there is no initial energy stored in the circuit, and we are asked to find out this I of t and I1 of t and I2 of t, and where we have solved this circuit and we have got these types of equation. Just to recapitulate this thing, just only we can remember this thing, that we have written this is this voltage source as a 336 divided by s, considering as a unit step is over there within this voltage, and this one as a L into S, this one is inductor is considered as L into S, and after that we have find out, we have considered the mesh concept, and then we have find out the equation for I1 and I2, and both the equation was in S domain, and after that we have taking the inverse Laplace operation, and then we have find out this equation, that is I1 of t and I2 of t. Now the our aim is Now our aim is to find out the initial condition of the circuit, and as in our question it is given that initially there is no more charge source, obviously we know that the value should be 0, obviously. So if we put the initial condition is 0, so then obviously we can only put that I of 0, that initial condition, it means t is equals to 0. So then 15 into e to the power minus twice 2t, it means e to the power 0, that means e to the power 0 means 1, so that will be minus 14. Similarly over here also e to the power minus 0, that will be 1 also, and u of t, that is u of 0 means 1, that will be the unit step. So obviously if we calculate it, it will be 0, and similarly for this I of 2, that will be I2 of t, and if we put t is equals to 0, then similarly these terms will be also 0. So as per the circuit criteria, we can see that from the Laplace equation or the inverse Laplace equation, whatever we have find out, we can see that I1 of 0 in initial I1 initial current at I1 and in I for I1 and I2 both are 0, that we can see. Okay. So now the next is, okay, so there is an question I can ask you, that if t is equals to infinite, at t is equals to infinite, the inductor behave like what? If we consider the infinite condition, then obviously at infinite condition the inductor behaves like a short circuit, that we have seen in our last problem, and in the problem that we will also look again. Okay. Okay. So this is our problem. We have already seen whatever the condition for the initial condition, it means whenever we have put I1 is equals I1 of t is equals to 0. Similarly for final value, it means at steady state condition, if we consider that t is equals to infinite, if we consider t is infinite, so I1 of infinite, it means just put t is equals to infinite, so e to the power some infinite, it means this term should be 0 and this terms will be also is equals to 0. So I1 value at infinite condition, that is 15 ampere. Similarly for this I2 of infinite condition, at infinite condition, it means we are putting this t is infinite and this t is also infinite, so e to the power some infinite data, that will be 0. So 7 minus 0 minus 0, that is 7 ampere. So one thing is clear, that at infinite stage the values of I1 and I2, that will be 15 ampere and 7 ampere. Now for the same circuit, as we have seen, the inductor behaves like a short circuit. So if we short this inductor, obviously the result should be same, right? So just sort it. So at infinite condition, the inductor, here is the inductor, so inductor is sorted and this one is also sorted again. So if we solve it again, this current is over here I1 and I2, again if we check it, so at t is equals to infinite condition, we can find out. So here 336 volts, so what will be the overall current? The overall current is nothing but we can find out the first overall resistance. So what will be the overall resistance? The 42 and 48, that is in parallel to each other, so the overall resistance is this one. So what will be this current? So this current will be, as this current we have considered as I1, so this current we can consider is equals to this voltage divided by this overall impedance. So voltage is 336 and our overall impedance, that is 22.4, and if we divide it, it is nothing but a 15 ampere. So we are getting here this current is 15 ampere. Now this 15 ampere current is being divided into two different part again. Now what will be this I2 current? So as this current is 15 ampere, so we are going to find out this branch current, so we can find out this branch current, that is equals to I2. We can write I2, just current is applying the current dividing rule. Which current is being divided? 15 ampere. So the 15 ampere current is being divided within 42 and 48 ohm resistance. So we are going to find out the current is 48 ohm resistance. So the other branch resistance was 42. So 15 into 42 divided by total resistance, where the current is being divided. Current is being divided among 48 and 42. So the denominator comes to 90. So it will be 15 into 42 by 90. 15, 15 6 are 90, and 6 7s are 42. So simply we can say the I2, that is 7 ampere. Okay, so I2 is equals to 7 ampere. So we can, so after getting this equation, one option is we can put t is equals to 0, we can get the initial values of the current. Similarly we can put t is equals to infinite, we can get the current value at infinite condition or in infinite time. This is one condition, and we have checked that at infinite condition the inductor behaves like a short circuit, and we have put that condition, and again we have calculated the data, and this data is same. We are getting I1 is equals to, for both the option, I1 is equals to 15 ampere and I2 is equals to 7 ampere. So we can consider that if any inductors are there at infinite condition, we will consider the inductor as a short circuit one. Now whatever the initial and final value theorem we have seen, now we will apply that initial value theorem and final value theorem for both the current, and we will check whether the result is same or not. Okay, so let's see what happened. Okay, so this one our actual equation in Laplace domain equation in S domain. This was the value for this I1 of S, and this one the value for I2 of S, and we are going to apply this initial value theorem and final value theorem to check the result is same or not. Okay, so for I1S, this is our function, or this is for our numerator by denominator option. So 40s by 360, that already we have seen in over there. Sorry, sorry. So this is our function, that I1 is 40s plus 360 divided by s cube plus 14s square plus 24s. Okay, so we are taking this one for the initial value and final value theorem. Okay, and our I2 value is this one. So first we will check the initial value theorem, then we will check the final value theorem. Okay, so if we goes forward for this initial value theorem, and as per the previous rules we know that the initial value theorem is states that when t is equals to 0. So and as per theorem it states that the value we can find out the value that is t tends to 0, at t tends to 0. So for this is our first function. So if we put the limit t is equals to 0, so I1 of t is equals to, if t is equals to 0, time tends to 0, so obviously our s tends to infinite, or if our t tends to infinite, obviously our s tends to 0, right? So if t tends to 0, I of t for initial value theorem, so limit s tends to 0, s into I of s, right? So if we put s is equals to infinite, s tends to infinite of this function, then just we are dividing this equation in we are breaking this overall function, okay. So we can write this function in this particular form, and whether after putting this value s is equals to infinite, we are getting that a 0, that the values of this I1 is 0 at t is equals to 0 or t tends to 0, it means at initial condition. So by applying the initial condition, again we are getting the I1 current value is 0. Similarly for I2 current, the initial condition, that will be also t tends to 0. Oh sorry, this is not infinite, so t tends to 0 for initial value theorem, and s tends to infinite, and this is our function. So it will be limit s tends to infinite, s into I of s. So limit s tends to 0, s into I of s, limit s tends to 0, and limit it will be I2 of t, and limit s into I2 of s, and that value is 168 divided by s cube plus 14s square plus 24s. So multiplied with s into I2. So 168s divided by s r cube plus 14s square plus 24s, and if we uh, rearrange the equation and so we are getting 168 by s square divided by 1 plus 14 by s plus 24 by s square in this equation. And if we put again s is equals to infinite, so this term should be 0. If s equals to infinite, this numerator portion should be 0 and this portion should be 0. S tends to infinite, so this overall portion will be 0 again, and this overall portion will be again 0. So this denominator portion will be 1 and the numerator portion is 0. So 0 by something, that is 0. So by applying the initial value theorem, again we are getting that the same result as we have applied directly from this equation, from the values of I1 of t and I2t. We have seen that initially I1 value at I1 of 0 is equals to 0 ampere and I2 of 0 is equals to 0 ampere. So initial value theorem satisfies our result. Now let's see the final value theorem. Okay. For final value theorem, as per theorem, this is our formation for this I1 of s, and equation is as per final value theorem. This is limit t tends to infinity I1 of t, or limit s tends to 0 s1 into I of s. So whatever we have written, it's given over there. So just simply we have multiplied it by s within this I1 of s term multiplied with s. It means just simply we have multiplied this by s. So if we multiply it, it will be 40s square plus 360s divided by s cube plus 114s square plus 24s. And if we rearrange the equation, this gives that 360 and put the limit s is equals to s tends to 0. So s tends to 0, this term should be 0. S tends to 0, this term should be 0. So s will be cancelled out. If we take a common of s, so it will be 40s plus 360 and it will be s square plus 14s plus 24. So this numerator, this should be 0. And this is 360 divided by this should be 0, this should be 0, 360 by 24, that is 15 ampere. And as per previously, we know that the result was 15 ampere. Okay. Similarly, for the I2s current, again we can see whatever the values are there, and as per the final value theorem, that is s tends to limit t tends to infinite, and obviously I1 of t, not I1 of t, this is I2 of t, and it will be I2 of s, obviously s into I2 of s. So this is the values of I2s multiplied with s. So s is multiplied over here, so taking s as a common, so it will be s square plus 14s plus 24. So s will be cancelled out, so numerator portion will be 168 and denominator portion will be this one. So if we put s tends to 0, so this term will be 0, this term will be tends to 0, and 168 by 24, that is 7 ampere. Okay. So already we have seen that I2 at infinite condition, that was is 7 ampere. Okay. That already we have seen over there. Okay. Look it over here. We derived it that I1 at infinite condition 15 ampere, I2 at normal infinite condition, that is 7 ampere, and at 0 there are 0 value I1 and I2. So by using this initial value and final value theorem, we can easily find out the value of the current, or to find the values of the voltage at initial condition or at infinite condition. Okay. Okay. So just to consolidate all the things, whatever we have seen regarding this circuit solution by applying the knowledge of this Laplace transformation, just whatever circuit is given to us, first of all we have to redraw the circuit. What we have to redraw? If the circuit having the inductance or having any capacitance, and if they are previously charged, or if there are any previous values of voltage or any previous value of current, so we have to change this inductor and capacitor based on our previous circuit. It means voltage source parallel with inductor, or current source parallel with capacitor, like that. And then whatever the voltage source or current source are given there, we have to take the Laplace transformation of that based on that sources. If there are any voltage sources, then simply just what we have did, we have considered as a step function. So the voltage sources value divided by S, that was the value, and then whatever the values of I1 of t and V of t, I of t and V of t in Laplace domain, we will consider as a I of S and V of S, and whatever the resistance, inductance and capacitance values are given there all together, or for each and every element we will consider the impedance and we will put it over there. Okay, and after that we will find out the overall equation for the S domain, and we will analyze the circuit in S domain, and after analyzing the circuit we will check the solution with initial value theorem and final value theorem, and after initial value and final value theorem we can take it as a inverse Laplace transform from S domain to time domain analysis, and we can put at t is equals to 0 to get the initial condition of the circuit, or we can put t is equals to infinite to get the response or the condition at infinite condition. And this initial value theorem result will be obviously same with this result, and this final value theorem result, that will be exactly same with this result if we put t is equals to infinite. Okay, so that's all for this. Thank you.